Welcome to another unit in this preparatory course Mathematics. This time with a unit on how to calculate extrema. Well, first off, we need to discuss what actually an extreme point or an extremum is. So here, before we start with this, well, we need to be first off able to calculate derivatives. Well, if we use the standard version, we actually need the first and second derivatives. So our function obviously must be differentiable for at least 2 times. And well, we could even expand this a little bit more. Needs to be continuously differentiable for at least 2 times. So we need continuous first and second derivatives. Well, once we have this, we then consider the first derivative and set this equal to 0. Why are we setting this equal to 0? Well, we can see this in the graph here. If we consider this function, we have 2 possible extrema. The one at -2 and the one somewhere around like 2/3 or something. And if you consider the slope, you see that before we get to the first extremum, so to the one at -2, the slope is positive. It's increasing the function. Afterwards, the slope is negative. The function is decreasing. And well, if before the slope was positive, afterwards the slope is negative, so function is continuous, so the slope needs to be 0, somewhere in between. This is actually, if you zoom into this maximum here, you see that at one point it becomes flat. So the tangent at this specific point is just like a constant. It's flat. So if it's flat, it has slope of 0, meaning first derivative is 0. And well, the same thing I argued for the maximum at -2 works for the minimum on the other side as well. Before the slope was negative, afterwards the slope is positive. So it means somewhere in between the slope needs to be 0. And that's actually at the point where the minimum is. So we call this the first order condition or the necessary condition. Here, however, we need to stress that not necessarily does having a first derivative of 0 this mean that there actually is a minimum or a maximum. Could also be a so-called saddle point. So it's increasing, becomes 0, but then it starts increasing again. As for example, if you consider the function f of x equal to x to the power of 3. That looks similar like this. So we need a second condition as well. That's the sufficient condition or the second order condition. This means that the second derivative needs to be different from 0. Well, still, we could have an alternative second order condition because, as I mentioned, with maxima, we have on the left positive slope, on the right we have a negative slope. With minima, on the left negative, on the right positive slopes. So we could replace this sufficient condition also by the so-called sign change condition. We're going to see about this in a moment as well. But first off, if we work with the sufficient condition via the second derivative as done here, then we can say if the second derivative is smaller than 0, so negative, we have a maximum. If the second derivative is larger than 0, then we have a minimum. And well, as I said, the problem is, what if the second derivative is 0? So then we cannot use this second order condition with the second derivative. Then we need to use the sign change condition, which I'm going to introduce in a few moments. And well, here we can also see something else. The blue function in this context, that's the original function we had. then the the parabola here, that's the first derivative, and the straight line, that's the second derivative. If we now consider the maximum on the left at -2, we see the function has a maximum here. The first derivative is 0. It intersects the x-axis, so it has a null there. And the second derivative, the line, is negative. So this works out fine. So let's have a look on the other side. Here I have a minimum. Again, I have a null for the first derivative, and the second derivative is positive, implying that this is a minimum. What we can also see here is that a function of degree 3 can, as is the case here, have two extrema, usually minima and a maximum, or can have no extrema, so would be a saddle point. If I have a function of degree 2, so a quadratic function, like here the first derivative, this only has one extrema, either maximum or minimum. And, well, straight line obviously does not have any minimum at all. So in other words, the maximum number of extrema is the degree of the polynomial, so the largest exponent, -1. So if I have a polynomial of degree 5, so the largest exponent being 5, this one can have either 4 extrema, 2 extrema, or 0 extrema, because that's the second rule. At most, degree -1 extrema, but then you can always subtract 2 of them. So degree 5 means has 4, 2, or 0. Degree 4 means it has 3 or 1. Well, that's basically what we can directly see or learn from this graph. Here again, I marked the two extrema. So what if the second derivative is 0? How do we find the extrema then? Well, I already motivated that we can use the slope, so the first derivative for this as well. Because if we take this function here, x to the power of 4 minus 5, then the first derivative is 4x to the power of 3, and the second derivative 12x to the power of 2. Obviously, if we set this first derivative equal to 0, we get a possible extremum at 0. If we were to insert this into the second derivative, we would get 0. However, if we were to draw this function, we would get what we have here on the right. So obviously, this part here has a minimum at 0, even though the second derivative is 0. So what can we do? We can use the so-called sign change criterion, meaning we select a value on the left of the possible extremum and one value on the right, and we insert both of them in the first derivative. So here we have the value of 0, so we select the minus 1 and we select 1. Minus 1 is smaller, 1 is larger than 0, and we insert them into the first derivative, giving us for -1, -4, and for 1, 4. In this context, we are only interested that the first one is negative and the second one is positive. We do not really need the values, only the corresponding sign. Because what we see here is that on the left, we have a negative sign and on the right a positive. So we have a minus plus sign change. This means we have a minimum. So this can always be used. However, when we have more than one extremum, we need to take care, because then the values we select are not allowed to be larger or smaller than any of the other extrema. We're going to see this in a different context later on as well. But first, let's take a note how this actually works out. We can have a plus-minus change, so increasing then decreasing, that's a maximum. Looks like this. Or we can have a minus-plus sign change. That's actually what we discussed in the exercise before. That would be minimum. Or if we do not have any sign change, so plus plus or minus minus, then this is a saddle point. So basically what we can say, if we summarize all of this, calculate first and second derivative, set first derivative equal to 0, solve for x. Insert x into the second derivative, find out whether this is positive or negative. Then we know whether it's maximum or minimum. If it's 0, then use the sign change criterion. Well, then basically you're finished with having found your extrema and classified them. So we can then consider an additional example here. So the 3 to the power x to the power of 3 divided by 4 plus x to the power of 2 divided by 2 minus x. So first we get the first derivative, which here is 3/4 x squared plus x minus 1, and the second derivative, which is 1.5x plus 1. Then we set the first derivative equal to 0. Here again, that's actually the example we discussed earlier. If we have the first derivative equal to 0, that's basically a quadratic equation for which we can use the midnight formula, which in our case gives us, well, as we saw earlier, the two solutions, -2 and +2/3. Those we can insert then into the second derivative. For -2, we get as a result -2 as well, which implies, as it's negative, that we have a maximum. If we insert 2/3, we get 2 as a result, implying that here we have a minimum. So in this case, we do not need the sign change criterion, because here inserting this into the second derivative works just fine. And well, that's then basically this example once from start to finish. And we can do a second, more practical example. So imagine we have a revenue function and we want to calculate for which price we get the maximum revenue. Well, here, as in many cases, I already suspect that there will be a maximum. So usually in economics, business administration, you already know that there will be an optimum, and you also know is this a maximum or minimum. But still, we're going to test this here. So we calculate the first derivative, which is minus 40p plus 400. Then we can solve for p, giving us a p of 10. And we calculate the second derivative, which here is just minus 40. As minus 40 is always negative, the result will always be a maximum. So we have a local maximum at a price of 10, which then is basically the solution to this exercise. Well, as I said, most cases we already know that this is a maximum because, for example, in economics, you usually assume that the revenue function is a quadratic function, which in the end would turn out, if the value before the p squared is negative, that it always becomes a maximum. Well, that's then all there is on the topic of extrema. So I say goodbye and see you next time.